video, we're going to look at weak acid problems relating to pH or Ka. So you're probably coming off of learning about how to do pH problems when it involves a strong acid. There are 6 strong acids: nitric, sulfuric, perchloric, OMI, HCl, HBr, and HI, so you should memorize those. And those problems are a little bit simpler in that if it's a strong acid, strong in chemistry means it 100% ionized. It's ionized. So in this case, if you have perchloric acid, which is the formula HClO4, for every one of these molecules, one H plus can be ionized. And therefore, since it's 100%, this concentration of the acid just becomes the concentration of H plus, which is great because it's a 1-to-1 ratio. So here's my concentration. 100% of it is in solution, so this translates easily to H plus. You could take the negative log of it and get the pH right away. Super, super simple. Now, if you have a weak acid, you can't do this because if I have a 0.04 molar solution of a weak acid, it does not 100% ionize. So I do not have a 0.04 or 0.04 molar concentration of my H plus. I have to find it in essentially what's going to be an equilibrium problem. So let's take a look and go through this a little further. So if you have a weak acid, it does not 100% ionize to completion. Therefore, we're going to put these double arrows. If this was a strong acid, I would put one arrow to the right, showing that it would 100% ionize into H plus, because if it's an acid, it's donating an H plus, so it's coming off, and its conjugate base, A minus. You could also write this as reacting with the water, where the water is a base. So if HA is the acid, water is the base, HA would donate an H plus, so it would turn into A minus, and H2O would accept the H plus as a base and turn into H3O plus. And these are essentially the same because if you notice, H plus and H3O plus are interchangeable. H plus doesn't really last by itself in water. It immediately joins with H2O to form H3O plus. So if I was going to write the equilibrium constant expression for these, and get used to writing an ionization reaction because you might have to. For an acid, you're just showing it act as an acid, donating an H plus. Either way I write this, I really get the same Kc because water is a liquid, so it drops out, and we really don't even have to worry about having one reaction or the other. I tend to write the first because it's easy to just pop off an H plus. What's actually really happening is it is reacting with water. So the second one is technically more accurate, but on the AP, you'll see the first one used a lot more. And we use acids so much that we're going to give this a special K. We're going to call it Ka. It's the exact same fraction. Products over reactants raised to the power that is the coefficient. But we're going to call it Ka for acids. And this is on your AP Chem formula sheet if you forget, but you'll probably use it so much that you won't forget. So what you'll notice is if I go back to this, the bigger the Ka, the more ions I have. It's more product favored. So the bigger the Ka, the stronger the acid. And in this case, the lower the pH will be for the same concentration. So again, the greater the Ka, the stronger the acid, the more it's going to ionize. And you can look up Kas for a lot of different acids. If you have a textbook, it's probably going to be in an appendix. And if you actually looked up Ka values for strong acids, you will see that they are super huge. They are so huge that we are going to assume they go to completion. So if I was ever to write the dissociation or ionization reaction, it would really just be an arrow all the way to the right, and it would 100% ionize. But these weak acids are not, and that's why you're going to see these small Ka values. Strong acids, we're not really going to see a Ka in the problem because you don't need it. It 100% ionizes. Okay. Also, what sometimes could be asked is which H is ionizing. You're going to see me practice this throughout videos, but you should see that the H that's ionizing should be connected to something more electronegative. So in this case, oxygen, fluorine, because they would hog the electrons and allow the hydrogen to come off as H plus. If you look at acetic acid over here, these H's are not ionizable because they are connected to a C. We assume this is a nonpolar bond, that the C and the H would have equal attraction for the electrons, so the H won't come off as H plus. So sometimes you could be asked about which H is ionizable. We figured I'd practice that now. Okay, so how do you calculate pH or how do you calculate Ka for a weak acid? So it's helpful to know that whenever you see a weak acid problem, it's an equilibrium problem. If you have to find the pH or if you're given the pH, this is all going to represent what is happening to the H plus at equilibrium, not initially, not initially, but at equilibrium. Let's look at a problem. pH of a 0.1 molar solution of formic acid, not a strong acid, not on my list, so I know it's weak, is 2.3825 degrees Celsius. It'd be a different pH at a different temperature, so that's why they give me temperature, though it's not really needed for this problem. Calculate the Ka. So right off the bat, if this were a strong acid, 0.1 would be my concentration of H+, because it would 100% ionize. And if I take the negative log of that, I would get a pH of 1. And you notice that here, the pH is not 1, it's higher. So a nice lesson to see right away is that for any weak acid problem, you're going to get a higher pH than you would for the same concentration of a strong acid because you have less H+ present. But anyway, let's continue this problem. Calculate the Ka. So again, this should be an equilibrium problem. They essentially give me 0.1 molar formic acid, which, that's to start with. Think back to equilibrium. What did I use when I had initial stuff in an equilibrium problem? I usually made an icebox. So that's what we're going to have to do. The only difference in this chapter is that they're giving me pH, or you have to solve for pH, which represents an equilibrium condition. So from the pH, I'm just going to write this, from the pH, you could always find the equilibrium H+. So it's not the initial H+, it's what you have at equilibrium. So if you're filling out an icebox, if you can get that into H+, that's what's going in your E column. It's helpful to always write the ionization reaction so we can see what's happening. If it's an acid, make it act as an acid. Get rid of an H+, donate the H+, and it turns into its conjugate base. Or you can make it react with water and it'll turn into the conjugate in H3O+, which is fine. We said H3O+, hydronium, and H+ are interchangeable. I'm just really specific about which H I removed. It should be the one connected to the oxygen, not the carbon. But if you wrote COOH minus, that's just getting nitpicky. Okay, and here's my Ka expression. We're eventually going to have to plug into this to solve for Ka, but right now I don't have all my equilibrium values. So let's go to an icebox to get that situated. So all I do is first I have to get my H+ concentration from the pH. 10 to the negative pH should give me the concentration of H+. This is what's going to go in my E column. So if I fill out my icebox, don't forget to put your reaction at the top. Some people call it a rice box. I think icebox sounds cooler, but don't forget to carry your reaction. This is the ionization or dissociation reaction for an acid. And initially it told me I have 0.1 molar solution, and I can assume I have 0 of my products because they would be none to start with. And as you put this in solution, some of it will ionize, not 100%. A lot of it's actually going to be found as the molecule version. And if I put in my change, minus x plus x plus x, go see a past video of mine if you don't know how to fill out an icebox. And now I can put in what I have at equilibrium, and oh great, we celebrate, we have a filled out column. 0 plus x equals 4.2 times 10 to the negative third. So I can see that x is 4.2 times 10 to the negative third, which means 0 plus x is the same. It's also 4.2 times 10 to the negative third. And 0.1 minus x. So technically I'm doing 0.1 minus this number, but what you should see is because these are weak acids, very little is going to ionize. So in my calculator, if I were actually to calculate 0.1 minus 0.0042, and I round to about 2 sig figs, I'm still going to get 0.1. You might get like 0.97, which is the same, 0.097, which is the same as 0.1. So you're going to start to see that we can actually simplify these problems more than we did even in the equilibrium chapter by saying, not a lot's going to ionize. My initial concentration of the acid is going to be basically unchanged. Now, I'm not assuming x is 0. I can't say these are zeros down here. But I can say that in comparison to 0.1, x is so much smaller that when subtracting it, it doesn't do much of a difference, which is very similar to those KSP problems if you've done them in the past. And again, if you have something different here for now, that's fine, but you're going to see you're going to get about the same answer. So now I have all my equilibrium stuff. I can plug into my Ka, okay? And I want you to start seeing this trend because we're going to derive a shortcut in a moment. H plus and my conjugate base, notice they have the same concentrations as long as this is a monoprotic acid, meaning as long as one H plus is released, it's a 1-to-1 ratio. So you're always going to get basically the H plus concentration squared in the numerator. It's almost basically like an x squared, H plus squared. And because we're using this assumption, which we actually call the 5% rule, and I'll get to in a second, we're using the assumption that the initial acid is basically unchanged. We can just say, oh, we're putting the initial acid concentration in the bottom. And this can start showing you that you can actually start to bypass an icebox as you do more of these. And we'll talk about them in a second. But solving this as it is, you get, here's my Ka, and notice it is small. A small percent does ionize. Now, another thing that they might ask you is something called percent ionization, and that's not on your formula sheet, so it is something to know. It's basically how much H plus has ionized from your initial acid concentration. So it's H plus at the equilibrium over the initial acid concentration initially, and timesing 100. And in this case, if I take my two numbers, I do get a pretty small number, and notice it is less than 5%. Now, technically, anything that's a weak acid is just something less than 100%, but you're going to notice a lot of problems are going to be less than 5%, and we'll chat about that in a moment. Another thing to notice about percent ionization is obviously the higher the percent, the stronger the acid, the more it ionizes. But if you look at this equation, the higher the initial acid concentration, because it's in the denominator, the lower your percent ionization. And that's a little counterintuitive, but if you increase the molarity of the acid, you're really not getting that much more H plus in comparison to the initial concentration, because we said X is so small, right, comparison to the HA, then your percent ionization goes down. And this is just a graph showing that. You increase the concentration, percent ionization goes down. I've seen a question asked on the AP before, so good thing to know. Okay, let's try the opposite direction. You might want to pause the video and try this. Calculate the pH of a 0.3 molar solution of acetic acid. Here's my Ka. Also calculate the percent ionization. Again, feel free to pause the video and check your work. It's always helpful to first write the ionization reaction. So this is an acid. It's only an acid. So all that's happening is it's donating an H plus. H plus is coming off, and you're getting the conjugate base. Feel free to write it where the acid's reacting with water, and you're getting H3O plus in the conjugate base, because the Ka expression is the same. It doesn't really matter which way you write it. I tend to go this way, your choice. And this is the Ka expression that eventually we're going to use. Again, they give me initial stuff. An icebox could be helpful. So I'm going to go to the icebox. I'm going to take my ionization equation, make an icebox. Initially, I have 0.3. This is 0, 0. Here's my X plus X plus X. They don't give me anything at equilibrium, so we got to make my E box in terms of X. This is 0.3 minus X. This is plus X and plus X. And I see if I plug into Ka as is, I would get a quadratic equation, which we don't like. So what do we say we can do to simplify this? We said rather than 0.3 minus X, let's assume X is so small because this is a weak acid, not a lot ionizes, and that my initial concentration is going to be relatively unchanged. So we'll just make this 0.3 instead. Again, we call this the 5% rule because for this to really work, you need, by the time you calculate percent ionization, you need a 5% or less ionization for this to be completely accurate. Now, if you have a little more than 5%, it actually is a pretty good approximation too. And most problems you see, you're going to use this just fine. So I'm going to make this 0.3 XX, and now I can plug into my Ka much more easily, not get a quadratic, and again, you should start seeing the same shortcuts start to happen. H plus and the conjugate base are exactly the same because it's 1 to 1, and you started with 0. So you're getting X squared on the top, or the H plus concentration squared. And again, we're not changing our initial acid concentration because of our 5% rule assumption, so this is just the initial acid concentration on the bottom. And you can solve for your H plus easily. Don't forget to answer the question. It wasn't about H plus, it was about pH. So we got to take the negative log of this and get the pH. And you should notice that, hey, the 5% rule does look pretty good because 0.3 minus 0.0023 is still about 0.3. Totally makes sense. But if I solve for pH, here's my pH, rounded to 2 sig figs, so I put 2 places after the decimal. And if I calculate my percent ionization, well, it is way lower than 5%. So that assumption was okay. And as I said, most of the time, it's going to be okay. Even if it's not okay, it still makes a pretty good approximation. And now that you know how to do this, you can actually do this for all other kinds of equilibrium problems where your K is super small. Just showing you without the assumption, if you were to actually calculate the X with a quadratic equation, you would get the exact same thing. So why do all that extra work when you don't have to? So obviously you don't know if it's 5% or less most of the time until after you complete the problem. So you might be like, well, when can I use the 5% rule knowing I can do it pretty accurately before solving the whole thing? And it usually works when the value of K is 1,000-fold, 10 to the 3 times smaller than the initial acid concentration. then it typically works. If you don't have an initial acid concentration, let's say you're trying to solve for that, then usually I find that if the K is around 10 to the negative fifth or smaller, it tends to work out pretty well. But I like this 1,000-fold rule. You'll see this come into play in some other acid problems we'll talk about with like polyprotic acids. So if K and the initial acid concentration differ by 1,000-fold, you're good. Okay, and like I said, now you can use this on any kind of equilibrium problem where you have a small K. Here's where I want to derive a little shortcut. Like we saw from the last problem, you're always getting this x squared on top. The h plus squared is on top. So rather than putting, in my Ka expression, rather than putting h plus times the concentration of the conjugate base, I can literally just make this h plus squared, or x squared. And on the bottom, rather than this as being the equilibrium acid, it's the initial acid, because we're using our 5% rule that very little ionizes is going to stay basically the same. So I could rearrange this Ka that's given on the formula sheet to looking like this to help me do problems more quickly and to completely bypass the icebox. If you're emotionally attached to iceboxes, keep doing them. You get the same answer. But if you want a quicker way, and on the AP we're always looking for quicker ways, then you can just do h plus squared over the initial acid concentration is equal to Ka. Some people like this version of the equation. A lot of times you're solving for pH, so I can rearrange this to solve for H+. I would take the HA, bring it to the other side, and then just take the square root. So these two are the exact same equation. This top one mirrors the Ka on the formula sheet a little better, so it might be easier to remember, but feel free to remember either one. You will not see these two circled equations on the formula sheet. If you're doing this on a free response, I highly recommend writing this equation first and then plugging in so the grader can see what you are doing and understand your work. So just showing you this last problem, I'm going to show you how I would have solved it with the shortcut. So I would say, okay, it might be helpful to write the ionization reaction to see that, yes, this is a monoprotic acid, obviously 1H for every one of these. So it has a small Ka, it's 10 to the third difference greater, smaller than my initial acid concentration. I can use my shortcut. So if I plug into my shortcut, and I'm going to use this version, H plus is equal to the square root of Ka times concentration at initial acid. So all I'm doing is I'm taking my 0.3, multiplying by Ka, and taking the square root, and boom, I'm done with getting my H plus. Totally bypassed doing an icebox and all the work there. So this happened much quicker, and now I just do the negative log, and I get a pH of 2.6, which is higher than the pH would be if this were a strong acid, because a strong acid would fully ionize. So take a moment, do some more problems, and see how you feel with this. You can also use a shortcut like this for bases, and we'll see that in another video.